In this video, we're going to talk about linear models, and this is referring to the ideas of lines. So linear is equating to a line, but what I really want you to think of it as is a type of consistent change, because that's what lines do represent, consistent change. In the last section, when we talked about proportional, not everything was proportional that we looked at, but all the examples actually that we graphed were lines. So lines is kind of a different relationship. It's a consistent change. Okay, let's look at an example. Population of a Midwestern city is 350,000 in 1990 and has been decreasing at a constant rate of 15,000 people per year. We're going to figure out a model that gives us the population after 1990. So the idea is when t equals 0, we're talking about years after 1990. So when you say t equals 0, that's literally 1990. When t equals 1, that's referring to 1991. And they're going to do the population in thousands. So when we label things on the table, 0 is actually referring to the year 1990, and 350 is representing 350,000 in the year 1990. So 1 year later, it's going to decrease by 15,000. Excuse me, I'm sorry. So 350 minus 15 is going to be 335,000, right? 2 years later, decrease by 15 again. That's 320. And again, 305. I would go ahead and keep completing this yourself. Like, go ahead and pause the video, finish it, do it yourself, and then compare your answers to mine, because it's just kind of good practice for you. So that's going to be 290. And then subtracting 15 again is going to be 275, 260. That'll be 245. And in an 8-year mark, it's going to hit 230,000. So 1998, it'll be 230,000. So they ask us to graph this. Now this time, they didn't label the tick marks for us. They did label the axes. So they told us the bottom one, the horizontal axis, is 1990. The vertical one is the population in thousands. So the bottom axis is easy. We're going to go 1, 2, 3, 4, 5, 6, 7, 8. Now, technically, it keeps going. I'm not going to end up probably filling those in right now, but it could keep going. I could keep filling them in if I wanted to. Okay, but for population, we should probably kind of look at what we have versus how many tick marks we have. So let's see, how many tick marks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tick marks. And we need to have a range between 230 to 350. So I think it'd be reasonable. We could probably start at 230. I almost feel like we should continue going lower than that, just because even though we're only be smart to make room for it to keep going into 14 years later, right? Like another 6 years after that. So I think I'm debating how I want to set this up. Typically, when you do this, you want to start at 0. So I'm kind of feeling like, let's see, 350, if you divide it by 25, if we went by 25,000, there's 14. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, there is 14. Okay, so I think that's what the thought was. Okay, cool. So we're go by 25,000. Screen while it was thinking. 325 and 350 for the top one. Sweet. Okay, here, I'm going to zoom out just a smidge so I can see both axes. Okay, so in year 0, it was 350,000. So in year 0 on this axis right here on the line, because technically this is 0, right? Right there is 0, even though I didn't label it. 350,000 is the population. In year one, it decreased to 335,000. So that's going to be closer to the 325. Maybe right about there. I have to do my best to approximate it. Year two, that was 320. So 320 should be pretty close to that one. Year three, it came out to 305, so a little bit above here. Year four, that was 290, so that one should be closer to the 300,000. Year five, that was 275. Year six was 260. Year seven was 245. And year eight was 230. Ooh, 230 would be like right about there. Okay, cool. All right. And if the pattern were to continue, I feel like my year five looks a little bit messy. Sorry, year five was supposed to be 275. Okay, so that should have been right on there. Looked a little messy. There we go. Okay. So if it were to keep going, it would go to 215 and then 200. So keeping that pattern up, 215, 200, it'll hit 200 right out here if it's going to keep the pattern out. Okay. And that's what I wanted to notice here is that there is a pattern. It is, first of all, lining up. Okay. They are lining up, and that lining up helps me kind of predict what's going to happen. But I did notice, I'm just going to point this out, that right here on this year and this year, it crossed very nicely, right? And that was a difference from year 0 to year 5. So I anticipated that by year 10, it would again repeat a nice number to plot. So year 15 would probably repeat a nice number to plot again, just saying. Okay, but I am going to draw a line. And since I'm freehanding it, my line is not going to be very pretty, and I'm sorry for that. But if you drew your line on your paper, use a ruler, make it nice and neat. All right. I can't do that with this. If I try to touch the screen, it'll mess everything up. So that's the best I can do on the screen. There we go. So there's our graph, and we do see some consistent change. So they ask some questions. What is the starting point? Well, in this case, the starting point is 350. But as a point, it would be year 0. So it would be the year 0, t equals 0, at population 350. But as an ordered pair, if I wanted to be cute, you might remember that we can write these points as ordered pairs, where the first number is indicating the number on the horizontal axis, and the second number indicates the number on the vertical axis. So if I really wanted to be cute, I could label that 0, 350. Now, what is the rate of change? Well, it's changing every year by 15,000. So we can say 15, but secretly it's 15,000. So let's write a formula we could use to calculate the population change. Now, real quick, I did want to comment. It's not 15. It's not like changing by 15. It's actually decreasing by 15. So if I want to indicate a decrease, I just kind of thought about it. I really actually want to make this a negative because it's subtracting 15 every year, or a negative 15,000. Okay. But I'm going to use the fact that we're talking about this graph. So 15 is really what we're talking about, even if it's 15,000. So if we wanted to write a formula, since the number of years in 1990, here's how we should do it. We should start with the starting point, and the change of 15 every year can be indicated by doing 15 times t. So in year 0, like let's check this formula. Let's make sure the formula works, okay? In year 0, when t equals 0, if I plug 0 in, I'm going to get 350 minus 15 times 0, which is just 350 if you plug that into your calculator. In year 3, let's pull year 3. Year 3, it would be 350 minus 15 times 3, which would come out to 305. So the formula works. If you plug in your calculator, it'll work. So what we did was we took the starting point in 1990 and I included the change, how much it's changing every year. And the change happens per year. So I times it by t because t is representing how many years have passed. That's how I came up with this formula. And I'm going to say this equals P for population. All right. Let's do another one. The population of a city in the Pacific Northwest was 150,000 in 1990 and has been increasing this time at a rate of 8,500 people per year. Okay, so let's determine the model. Again, using years after 1990. All right, this time then, t equals 0 is going to be 150. So it's going in thousands. So year 1, it'll be 8,500. So that's going to be 158.5 if I'm going by thousands. So 158.5 in thousands is 158,500. So I'm basically adding 8.5 each time. So for this, 8.5 is how we measure that in thousands. Okay, so adding 8.5 again, I'm getting, 158.5 plus 8.5 in my calculator gave me 167. I don't know why I'm not trusting myself, but I'm not. Okay. And then add 8.5 again. It's going to be 175.5. And then that's going to be 184. 8.5, 192.5. And that'll be 201, 209.5, 209.5 plus 8.5. Sorry, sometimes I have to like talk myself through it. Comes out to 218. All right, there we go. Okay, so we've got our table. Let's do a graph. Now this time, I can do the 0.5s. I can, but I'm not as eager to do 0.5. Okay, so I might skip every other one. Just kind of thinking about that out loud. This time also, I don't have to go as high. I'm only going up to 218. So let's just see. Tick marks here will still go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the year 2000. And so forth. Okay, so I still think there's 14 tick marks. So if I need to get to 200, round that to 220 divided by 14, about 15 each time. All right, so if I 15 times 14, that comes out to 210. Yeah, it's a little bit shy. So maybe I'll go by 20s. 20s aren't too bad. We'll go by 20s each time. Okay, so first one here is going to be 20, then 40, then 60, then 80, 100, 120, 140, 160, 180, 200, 220, 260, 280, 300. So it kind of makes more sense to go ahead and go higher on this one, get up to 300, because this is a population of growing, right? So the trend is that it's getting bigger. So it makes sense to go substantially above the values that we're going to see or plot that we have. Okay, so in year 0, it was 150,000. So right smack dab in the middle. But I might skip every other one. I don't know. One is 158.5. You know what? I'm just going to suck it up. 158.5 is going to be like real close to 160. And then it goes to 167, which should jump a bit. It goes 175.5. 175.5 is going to be closer to the 180. I feel like that one. It's kind of sloppy looking. There we go. Okay. And then at year 4, we're at 184. Year 5, 192.5. Year 6, 201. That's practically 200. 209.5. And 218 right below. Okay, there we go. It's the best I could. And if I were to draw a line, of course, my line is going to be a little bit wiggly. Keep growing out there. Looks like it'll hit 300,000 somewhere in 2004, 2005, somewhere in there. All right, if I did a good job of drawing that line. So what is the starting point? Well, this time the starting point was 150. Or as an ordered pair, it would be 0, 150 as an ordered pair because t equals 0. I had a population of 150. Okay, what is the rate of change? This time it was changing by 8.5, which represented 88,500. So a formula would be the 150 plus 8.5 per year. So a linear model is a formula, graph, or table which represents a quantity that's changing at a constant rate. For this, our tables were always changing by a constant addition or subtraction, and the graphs were changing at a constant increase or decrease, and therefore it formed a line. Even if my lines aren't perfect, it does line up. Okay, so we could use linear models to represent a bank account that is steadily decreasing or steadily increasing. Let A represent your bank account and T represent your time. So if your balance is represented by A equals 600 minus 120T, so T is time in months. So every time T is increasing by 1, another month has ticked off. So write a sentence explaining the meaning of the starting point. So if I'm kind of equating it to what I did before, the starting point is the first number I wrote. So the starting point would be 600. So 600 is the amount in the account when you begin this. So $600 is the initial amount in the account. Now, the rate of change is the second number. And in this case, I notice we're minusing 120. So like before, when we were decreasing in our population, this would represent a decrease in the bank account. So it's going to decrease. Sorry, I'm writing negative 120 is a decrease of $120 per month. So how much is going to be in there in 3 months? Well, that's going to be plugging in T equals 3 into the formula. I'm going to get A equals 600 minus 120 times 3. Plugging that into my calculator, I'm going to get 240. So the answer is $240 since we're talking about money. So how long is it going to take before this thing equals 0? Well, if I keep subtracting 120 from 240, right, that's going to give me 2 more months, and then it's going to hit 0. So 5 months. 5 months. Oops, that's not how you spell month. 5 months, because if I keep subtracting 120 from that, it's going to decrease. Or I notice if I plug 5 in for t, it's going to give me 0 when I plug that in. Okay, 120 times 5 is 600. And 600 minus 600 comes out to 0. So 5 months. But I use the rationale that if I keep decreasing by 120 per month, after this number, I'd have to subtract it 2 more times, which meant 2 months. That's what I did, how I figured that out. Okay, if you are recognizing, or sorry, if you're looking at the equation of a linear model, how can you recognize the starting point? How can you recognize the rate of change? So the starting point tends to be, often it is the first number, but it's really the one that is just a number. It's the one that isn't with the variable. It's the one that's by itself, right? The 600 is kind of standing alone. But the rate of change is multiplied by the variable. So that's how I tell the difference. So the way I tell it is the starting point is a number by itself. And the rate of change is the one number next to the variable, or multiplied by the variable. That's how I tell the difference. Okay, so for 13 and 14, let's write an equation and let's define the variables that we use. So this time they're not going to give us our labels. We'll have to come up with the labels. Baby was born weighing 7 pounds. She's been gaining 1.5 pounds every month. Okay, so month, that's going to be my T, my time. And my equation is measuring then how many pounds she's gaining. So I guess I could call that W for weight, or if you want P for pounds, whichever one you prefer. I'm going to go ahead and go with W. I like the idea of W for weight in pounds. I'm going to put in parentheses LBS for pounds. So it's the weight in pounds, and T is the months. So since they start at 7 pounds and increase by 1.5 pounds per month. By the way, you could have used M for months if you really wanted to, and you could have used P. Like I said, it really doesn't matter. You're creating your own variables. I just happen to like W and T, weight and time. That works for the next problem, by the way. If I do T again for month and W for weight. Athlete weighs 230 pounds. He plans to lose 3 pounds per month. So 230 minus 3 pounds times T. All right. I'm almost tempted to change it because why not? I just want to show you that it doesn't matter. I'll call that M and I'll call that P for pounds. Why not? I just want you to know it really doesn't matter. So P and M, you don't have to change it if you already wrote it and you don't feel like it, but I want you to know they're the same thing. I can create whatever variables I want. Is it realistic to expect that the rate of change will remain constant in these situations? Well, no. First of all, when you're talking about a baby doesn't keep gaining weight at that rate forever, right? I mean, they may change too, depending on their age. So the answer would be no. First of all, a baby doesn't gain weight at that same rate forever. Because otherwise, if they just keep gaining weight forever and ever, right, we never stop growing. And though it feels like that sometimes, that is not the case. And for the athlete, of course, there comes a point where your body just doesn't want to lose any more weight, starts holding on to weight, right? Otherwise, you're going to kill yourself and you never reach a weight of 0. So same thing, like you can't lose an athlete and an athlete can't keep losing weight forever. Plus, we know that the body loses weight at different rates, depending on how much you have to lose, depending on the program you're following. Weight fluctuates as you lose it. It's not always constant. Okay, we get that. That's the idea. But it's a rough estimate of how it could look. All right. Make a fairly accurate sketch of the graph of the linear model 600 minus 120t. Put months on the horizontal axis because the balance depends on the number of months, and label and scale both axes. So now this time they're asking us to create our labels rather than give it to us. So the horizontal axis, they already told us that's going to be our months. Here, I'm going to do this in blue. So this one is months, and we'd be using t for that variable. The vertical axis is going to be A for the amount in the account. And that would be measured in dollars. All right. And since, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8 tick marks that way. Taking the 600 and dividing it by 8, that gives me approximately 75. Perfect. So I'm going to go by 75 for each label here. So this is going to be 75, 150, 225, 300, 375, 450, 525, and 600. So kind of ran into the writing there. That's all right. Okay, so months, I already know it's not going to go beyond 5 months, right? This thing's going to hit 0 in 5 months. I could just go 1, 2, 3, 4, 5. I could. There'd be nothing wrong with that. But since I have the space, I kind of feel like skipping every other one. So in other words, I'm going to kind of do every 2 of them is 1. Oops. 2, 3, 4, 5, just because I have the room. All right, there we go. So there's my axes. I've labeled them. I've scaled them. I'm ready to graph. So at month 0, which starts right here, that axis, we're at $600. And when we subtract 120, we got to 480 in month 1. So month 1, if I subtract 120, I get to 480. So I literally calculated that this comes out to 480, which is going to be close to the middle here. So I plugged in t equals 1, and I got 600 minus 120 times 1, which came out to 480. And then I know the next month they're going to lose another 120, right? So if I subtract 120 from here, that's going to be 360. So 360 is next, which would be closer to the 375 on that one. Maybe even a little closer. Okay. 3 months, it's going to subtract 120 again. That's going to be 240. 240 should be closer to the 225. 4 months, if I subtract it again, it's going to be 120. That might be pretty close to halfway, actually. And then at 5 months, it hits 0. And there we go. So if you don't put any money in 5 months, you're going to run out of money in that account. And that just kind of shows how we can graph that scenario and know that anything beyond that, they're going to start getting dinged, right? Start paying fines for going overdrawing on the with the account. And there you go.